All right, today we're jumping into a fantastic cosmic detective story. The star of our show is a pulsar, a super fast spinning star called B2021+51. And it's way out there, a staggering 4,080 light years away. Now, for a long time, we thought we had its origin story figured out, a really dramatic tale of cosmic twins. But as you know, with any good mystery, it just takes one new clue to change absolutely everything. And it all kicks off with this, a scientific paper from 2004 with a headline that sounds like it was ripped right off a movie poster, Separated at Birth. And this wasn't just some catchy title, no. It was a serious, compelling theory about our pulsar and its supposed sibling. It really set the stage for this incredible story of a family just torn apart by one of the most violent events in the universe. So here's the story that everyone believed. You had Pulsar B2021+51 and another one, B2020+28. The idea was they used to be partners, a binary star system, orbiting each other for millions of years. And then, boom, a catastrophic supernova explosion happens and flings them in opposite directions across the cosmos. I mean, it's a powerful, almost poetic origin story. And if you're wondering why this theory was so convincing, well, just look at the evidence they had at the time. Their ages were nearly identical, right around 2.8 million years old. Their magnetic fields were in the same ballpark. And here's the kicker. They were both found in the same patch of sky, the Cygnus constellation, and they seemed to be moving away from the same point. On paper, it was a perfect match, a real slam dunk. But okay, a good story is one thing. How do you actually prove something like that happened millions of years ago? Well, this is where astronomers basically become cosmic detectives. To check out a claim this big, you can't just look at where things are now. You have to trace their movements all the way back in time. And to do that, you need some seriously precise tools. So first up, a super quick refresher on what we're actually tracking here. A pulsar is what's left after a giant star goes supernova. It's this tiny, incredibly dense core that's spinning ridiculously fast. And as it spins, it shoots out beams of radio waves from its poles. For us here on Earth, every time that beam sweeps past us, we get a pulse. It's just like a cosmic lighthouse. Now, to trace a pulsar's path, you first have to know how far away it is. And the absolute gold standard for that is a technique called parallax. You can actually see this for yourself. Go ahead, hold your thumb out in front of you. Now close one eye and then switch to the other. See how your thumb seems to jump against the background? Astronomers do the exact same thing just on a much bigger scale, using Earth's orbit around the sun to measure that tiny shift for a star. It lets them nail down its distance. The second piece of the puzzle is proper motion. This is basically just the star's slow drift across our line of sight over many, many years. So when you combine its distance, which you get from parallax, with this sideways movement, you can figure out its true speed and direction. And once you have that, you can hit rewind and trace its journey all the way back through space. And this is where our detective story gets a major plot twist. Fast forward to 2015. A new team of scientists comes along with some serious hardware, the European VLBI network. It's a whole bunch of radio telescopes working together as one giant eye on the sky. And they remeasured everything with a level of precision that was just impossible back in 2004. And what they found was a total game changer. Just look at this table. The new parallax measurement was completely different, and that meant the calculated distance was way off. It wasn't 2 kiloparsecs away, it was only 1.25. That's almost twice as close as we thought. In detective terms, this is like finding out your suspect's alibi was for the wrong city entirely. It blows the whole case wide open. So what happens when you plug these new, much more accurate numbers into the models? Well, the whole story falls apart. The pulsar's real speed, its real direction, it was all different. So when the astronomers reran the simulations, tracing the paths back in time, they didn't meet up anymore, not even close. That whole beautiful, poetic story of cosmic twins just evaporated. So just how unlikely was the twin theory now? The 2015 simulations delivered the knockout blow. The chance that these two pulsars could have come from the same system was now a tiny, vanishingly small 0.06%. It's basically a no way. Case closed. At this point, the conclusion was undeniable. They weren't twins. They were just two random pulsars that happened to be in the same celestial neighborhood. But, you know, this isn't a failure. This is a perfect example of how science is supposed to work.
A beautiful story is great, but it always has to give way to better evidence. You follow the data no matter where it leads.
So the old case is officially cold, but that pulsar is still out there, spinning away. So is that the end of its story? Does it have anything new to tell us? It turns out it absolutely does. Because now that we know exactly where it is, scientists have figured out a completely new and exciting way to use it. And that brings us to the latest chapter in this pulsar's life, coming from a recent study using the absolutely colossal FAST telescope. Now, scientists aren't looking at the pulsar's history anymore. Instead, they're using its light as a probe, like a cosmic flashlight, shining a beam through the dark to illuminate all the invisible stuff between us and it. And the technique they're using has this really cool name, interstellar scintillation. It might sound complicated, but I promise you've seen this effect yourself. Think about the way the air shimmers over a hot road, making things in the distance look all wavy. It's basically that, but on a galactic scale. The pulsar's radio waves pass through these clumpy clouds of plasma out in space, and that makes its signal twinkle. Here's how this whole thing works, and it's pretty clever. First, our pulsar is out there sending out a perfectly steady, predictable beam, just like our lighthouse. But as that beam travels toward us, it has to pass through these invisible screens of turbulent plasma. By the time that signal reaches our telescopes here on Earth, it's all distorted and twinkling. And here's the brilliant part. Scientists can analyze the pattern of that twinkle to map out the location and properties of those plasma screens that are otherwise completely invisible. And this is already giving us incredible results. The research using FAST was able to pinpoint the main plasma cloud that's messing with B2021+51 signal. They found it's located 887 parsecs away from us. That's over 2,800 light years, about 2/3 of the way to the pulsar itself. Think about that. By doing this with pulsars all over the sky, we're literally starting to build a 3D map of the stuff floating around in our own galactic neighborhood. So the story of Pulsar B2021+51 has been completely transformed. Its old identity as a separated twin was a great story, but it was debunked by better science. And in its place, it's become this incredibly valuable tool, a flashlight that's helping us chart the unseen structures of the Milky Way. It just makes you wonder, doesn't it? How many other stories that we think we know are out there just waiting for one new clue to rewrite everything.